Chapter 25.3, Wave Motion. Most of the information around us gets to us in some form of wave. Sound is energy that travels to our ears in the form of one kind of wave. Light is energy that comes to our eyes in the form of a different kind of wave, an electromagnetic wave. The signals that reach our radio and television sets also travel in the form of electromagnetic waves. When energy is transferred by a wave from a vibrating source to a distant receiver, there is no transfer of matter between the 2 points. To see this, think about the very simple wave produced when one end of a horizontally stretched string is shaken up and down. Figure 25.5. See the string, and the hand is shaking it up and down. These pulses are going to travel down the string. After the end of the string is shaken, a rhythmic disturbance travels along the string. Each part of the string moves up and down, while the disturbance moves horizontally along the length of the string. It is the disturbance that moves along the length of the string, not parts of the string itself. In the box here it says, doing physics, making waves. Oscillate a marking pen back and forth across a piece of paper as you pull the paper in a direction perpendicular to your motion. You'll get a curve that may resemble a sine wave and will have a certain wavelength. What happens to the wavelength when you pull the paper faster? Next, repeatedly dip your finger into a wide pan of water to make circular waves on the surface. Will the wavelength of the waves increase, decrease, or remain the same when you dip your finger more frequently? Drop a stone in a quiet pond and you'll produce a wave that moves out from the center in an expanding circle. Figure 25.6. It is the disturbance that moves, not the water. For after the disturbance passes, the water is where it was before the wave passed. When someone speaks to you from across the room, the sound wave is a disturbance in the air that travels across the room. The air molecules themselves do not move along as they would in a wind. The air, like the rope and the water in the previous examples, is the medium through which the wave energy travels. The energy transferred from a vibrating source to a receiver is carried by a disturbance in a medium, not by matter moving from one place to another within the medium. Section 25.4, Wave Speed. The speed of a wave depends on the medium through which the wave moves. Sound waves, for example, move at speeds of about 330 meters per second to 350 meters per second in air, depending on the temperature, and about 4 times faster in water. Whatever the medium, the speed, wavelength, and frequency of the waves are related. Consider the simple case of water waves. Imagine that you fix your eyes at a stationary point on the surface of water and observe the waves passing by this point. If you observe the distance between crests, that's the wavelength, and also count the number of crests that pass each second, that's the frequency, you can then calculate the horizontal distance a particular crest moves each second. So in the example, the bird is looking at the waves. The crests are 1 meter apart, that's the wavelength, and the V, that's a V, is equal to 1 meter per second. That means the crests are moving 1 meter per second. For example, if the wavelength is 3 meters and 2 crests pass by a stationary point each second, then 3 times 2 meters of waves passes by in 1 second. The waves therefore move at 6 meters per second. We can say the same thing this way. The wave speed is equal to the wavelength times the frequency. Or in equation form, v for velocity is equal to lambda times f. Lambda represents wavelength, f represents frequency. So it says v is wave speed, the Greek letter lambda is wavelength, and f is the frequency. This relationship holds for all kinds of waves, whether they are water waves, sound waves, radio waves, or light waves. Table 25.1 shows some wavelengths and corresponding frequencies of sound in air at the same temperature. Notice that the product of wavelength and frequency is the same for each, 340 meters per second in this case. During a concert, you do not hear the high notes in a chord before you hear the low notes. The sounds of all instruments reach you at the same time because they travel at the same speed. Notice that long wavelengths have low frequencies, short wavelengths have high frequencies. The wavelength and frequency vary inversely, that means oppositely, to produce the same wave speed for all sounds. So let's look at the table. 25.1 sound waves. The first one has a wavelength a little over 2 meters, a frequency of 160 hertz, and it travels at 340 meters per second. If we go to the bottom of the list, this one has a wavelength of only 0.6 meters, a much shorter wavelength, and it has a much higher frequency. When you multiply them together, wavelength times frequency gives us the wave speed. It's still 340. So this is showing us that sound waves all travel at the same speed, even if they have different wavelengths and different frequencies. Computational example. If a train of freight cars, each 10 meters long, rolls by you at the rate of 2 cars each second, what is the speed of the train? This can be seen in two ways, the Chapter 2 way and the Chapter 25 way. From Chapter 2, recall that velocity, v, is equal to the distance divided by the time. 2 train cars, 10 meters each, is a distance of 20 meters, and the time it takes is 1 second. It says right here, each second. So 20 divided by 1 equals 20, so the velocity is 20 meters per second. Here in Chapter 25, we compare the train to wave motion, where the wavelength corresponds to 10 meters, and the frequency is 2 hertz. If we multiply the 10 meters times 2 hertz, we get the same answer, a wave speed of 20 meters per second. Just like up here, we calculated a speed of 20 meters per second. One of the nice things about physics is that different ways of looking at things produce the same answer. When this doesn't happen and there is no error in computation, then the validity of one or both of those methods is suspect. Here are a couple questions. Number 1. If a water wave vibrates up and down 2 times each second, and the distance between wave crests is 1.5 meters, what is the frequency of the wave, what is the wavelength, and what is the wave speed? Okay. It vibrates up and down 2 times each second. That means it has a frequency of 2 hertz. The distance between wave crests is 1.5 meters, so that's the wavelength. If we multiply those together, using the formula from above, wavelength times frequency, we multiply 1.5 times 2, which gives us an answer of 3 for the speed. The speed is 3 meters per second. Number 2, what is the wavelength of a 340 hertz sound wave when the speed of sound in air is 340 meters per second? Okay, 340 hertz. Hertz tells me that this is frequency. The speed is 340 meters per second, so that's my v, my velocity. So let me look up above. V is equal to wavelength times frequency. I know the v is 340. I know the f is also 340. And then we have to figure out what wavelength is. So what number times 340 equals 340? Yep, 1 is the answer. So the wavelength must be 1 meter. Let me show you that one more way. So here's the formula that we picked. We identify the 340 as our v, our velocity. The frequency is 340. Our clue was that it was hertz. So when I rewrite 340 for v, I rewrite 340 for f. The equation looks like this. So this is wavelength times 340 has to equal 340, so the wavelength must equal 1 meter. Thank you.